the next lesson? Conditional probability? Okay. Who are we missing now? Yeah, he emailed me. Who else? Let's see. Who else are we missing? Is it just the same?
Yeah.
I'm just double checking. David? Oh, great. Baraka. Patrick. Okay. Right, now, what we're having a look at in the first class is a thing called conditional probability. So, I have an example here. Let me think of the example. Yeah. That's glasses. So, you have two people, two ladies, one without glasses and one with glasses. So in the first case, I ask you, okay, what's the probability that this random person, this random lady you meet is a librarian? So whatever the probability is, we'll just say it's P1. And then likewise I say, what's the probability that this random lady you meet with glasses is a librarian? P2. So can you see how they're both different questions? Because in both cases there's an extra piece of information. In one case there's an extra piece of information that you know that you didn't know in the first case, right? So the way we distinguish that is we say the probability that this woman here is a librarian, so L, that's that one there. Whereas this one here is the probability that she's a librarian. But you have an extra piece of information, don't you? And we represent that with a vertical line. And she has glasses. So what this here means is, given that, you know that this person has glasses. Maybe this person has glasses, but they're just not wearing it. You don't know if they have glasses or not. All you know is they're not wearing their glasses if they do have it. Okay? So it's not even right for me to say that this first person is a person without glasses. Just know that they are not wearing them right then and then. So this is called a conditional probability. Another example would be, what's the probability it'll rain tomorrow? So, whatever number it is, we understand that that's different to the question, or that's a different calculation if I say, what's the probability it rains tomorrow, given that we had rain today. These are called conditional probabilities because you have more information, more conditions. Does that make sense? Yeah? Yeah. Let me have a look. First let's do the formula for it. Let's try and represent this on a Venn diagram. So if this is A and this is B, I would like to know what would be the probability of A given B. So, one thing you know for certain, has B happened or not? Definitely know B has happened. Okay? So, in some ways, the rest of this diagram now is deleted. Is there any possibility that we're outside of B? Yeah, we can't be. There's one thing we know for certain, is that we're inside of B. Okay? And the probability of A is only now going to be this piece here. And not A is going to be this piece here. So you might say, oh, okay, so this is A given B, that must be this here. And you'd be nearly right, but there'd be a small problem. Let's just put in some numbers as an example. So let's say this is 0.1, 0.2, 0.3, and here is 0.5. Why is this not 0.2? Well, let's have a look at the other one. What would be the probability of not A given B? Well, we think maybe it's 0.3. But what's the problem here? Do these add up to 1? No, and should they? They should still add up to 1. So it's not quite 0.2, but it's nearly 0.2. There's a small correction you have to make. Any ideas? Anybody knows what it is? It's over something. Over what number? Over, yeah, so what number? Yeah. The formula. We can get to that in a second. You see, in some ways we have to change this into a new Venn diagram. What did I say here? Sorry, 0.5, 0.2 and 0.3. We're now only looking at B, and that's all that exists. And we split B. We have an A piece and a not A piece. We can't say 0.2 and 0.3. We have to say 0.4 and 0.6. Why? Well, it still has to add up to 1. And can we be outside? No. We know we definitely have B. So this process, we call it renormalize. It means you make the probabilities add back up to 1. Okay? Now, if you want it as a formula, like this is what you were asking me, David, you can give the formula like this. The probability of A given B is the probability of A and B, the intersection, divided by the probability of B. Now, this formula should look familiar. I think we did this in the lesson on tables, didn't we? So we found the formula using Venn diagrams. Okay, what was your question?
Can you make the 8 0.6 and then
0.6 and 0.4? No, it has to keep the same proportion. Which is bigger here? The B. It has to keep the proportion the same. Okay, can you write that bit down? Can I? No. Okay, can I scroll down? Yeah? Can I scroll down? Yeah, okay. Right. I'm going to draw a Venn diagram and then I'll just ask you a couple of questions on it. So there's two sets here. We'll say male and accepted. So the example I'm imagining here is, let's say, university applications. Okay, so let's say point 3, point 2, point 25, and what is that, 6? So that must mean here is point 1.525? 25, thank you, yeah. 25. Okay. So I'll say a couple of questions and I want you to calculate. So M represents male. So if you're not inside M, then what are you? Female. Okay. We are considering only 2 genders for this class. Right? And A means you've been accepted for university. And if you're not inside A, then that means not accepted. So my first question will just say, what percentage of applicants were male and accepted? So what's male and accepted here? Male and accepted. That is 0.2. So if you had 100 random students, how many of them would be male students and accepted? 20%. Okay. Yeah. What is the probability that you pick someone at random and they're both male and have an acceptance offer for university? It's 20%. Oh, male and accepted, intersection, 20%. Yeah? That's okay? Is that the same thing as saying 20% of men who applied got into university? No, it's not. So how would I write that down? Why would I write that? I want to know if you're male, what's your chance of being accepted into university? A, yeah? A given M. So you're just looking at the males and you want to know the probability of being accepted. Okay, so what would that be here? Well, according to my formula, it would be 0.2 over 0.5, which in this case is 0.4. Do you have the formula written down? What's the formula? No answer? Okay. Continuing. Right. What is the probability of being accepted and female? What's on the top here? No? 0.25. They are accepted females. Yeah? And on the bottom? 0.5 again. But how did you get 0.5? What did you add? True, yeah, but what did you add? 0.25 and 0.25, because these are outside male. So what do you get here? 0.5. And then lastly, probability of being female and accepted. So What's that one here? 0.25. Now, what I want you to see is those four numbers are obviously different, but it doesn't seem like there's much of a difference between what I'm saying. Like here I'm saying male and accepted, and here I'm saying the probability of being accepted if you're male. Doesn't sound like much of a difference, does it? But you can see that they are different. And here, probability of being female and accepted. And here, probability of being accepted if female. So you have to be really, really careful with the language here. It's not as straightforward as you might think. You have to really read the sentences carefully to make sure you're calculating the right thing. Yeah, we'll do another example. So, I think I'd like you to write that down, but I think it'd be a good idea if you can put a sentence maybe on this one and maybe on this one. So, what did we say this one was? Male and accepted. Whereas this one is if male, yeah. Yeah. It sounds like the same thing, but it's not. Which one, Nikita?
Accepted.
Which one? 1, 2, 3, 4.
Second one.
Probability of being accepted if you're male. So you can think about it like this, like I said before. If you have 100 people, 50 male, 50 female, 20% of your group will be men holding an acceptance offer. And 25% of your group will be women holding an acceptance offer. If you only look at the men, so just take this group out, 40% of the men will be holding an acceptance letter. And if you only look at the women, 50% of them will be holding an acceptance offer letter. Okay? We'll do another example. Can I scroll down? So, let's see. So another example might be D represents people with the disease, and S represents the symptoms of the disease. Okay. This time I'm going to go backwards. I'm going to give you the probability. So we'll say that 20% of the people that present have the disease. We'll say 15% of people who present have symptoms. And we'll say that let me see, I want to give a given one. The probability of having the disease, given that you have the symptoms, we'll say is 50%. So, at the hospital, what percent of people present with the disease? 20%. What percent of people present with symptoms? 15%. And then the last one is, among the people with the symptoms, how many of them actually have the disease? Half of them do. Yeah? The people who have the symptoms, half of those people have the disease. Yeah? So let's take let's take a disease like that Chinese flu virus thing at the moment. Yes, that's the one. You know, just because you have the symptoms doesn't mean that you have the disease, right? So maybe half the people with the symptoms actually do have the disease. Okay? I'm not sure what the numbers might be, but something like, actually that's maybe a little bit high, because I would imagine most of the time people with the symptoms don't have the disease. Because the symptoms seem to be very generic, aren't they? Yeah. High fever, shortness of breath, something like that, you know. So in that example, 50% would be way too high. Unless maybe you're in an at-risk area, then maybe it would be true. Okay, I'll give you a minute. Your job is to fill the numbers back into the Venn diagram here. See if you can figure that out. My tip is you should start with this one, most useful one to start with here. You got that? Yeah? You got that, guys? Okay. Almost, okay. Can I scroll down? Yeah? So, let's have a look. Remember I said the bottom one is the most useful. Do you remember the formula? It's P, disease and symptoms over symptoms. Now, actually, we know what symptoms are. What are they? 1.5. So, if you cross multiply 0.0 0.5 times, yeah, 0.075.
Yes.
Now, disease adds up to 20%, so this one here would be 0.125, is it? No. Okay, and then symptoms have to add up to 15, so that would be 0.075. So what's left outside here? 725? Pretty big. So how many people are disease-free and symptom-free? 75%. Yeah?
Wait, how did you get 725?
Tell me how I got it.
Huh?
You know how I got it. As you do. What must the total probabilities add up to?
What?
And if I know the other three probabilities?
I add.
And then? From? Okay. Right. Can I scroll down? Okay. Now, we'll go back, we'll do another example, a couple more examples, but I just want to remind you of some terminology. So you remember from biology that when you have a test for a disease, it's not going to be perfect, right? So, what's the word that describes the probability for having a true positive? Remember, true positive means the person tests positive and they actually have the thing that you're testing for. What's the word for that? Do you remember? It begins with an S. We say it's the something of the test. Do you remember? Oh, no. No. No, you forgot. The sensitivity. Remember? So if I say the sensitivity is 90%, what am I saying? That the true positive rate is 90%. Which means if you test positive, what's the chance of having the disease? Oh, sorry, I said that backwards, isn't it? If you have the disease, what's your chance of testing positive? 90%. And what's the other one? The true negative result. What's that one called? No, it also begins with S.
Sensitive.
No, we just use sensitive, so it can't be that one again. Not sensitive begins with N for not. Specific. Yeah. So if the test is 90% specific, that means if you don't have the disease, what's the chance of getting a negative result? 90% in this case. Okay, if I said the test was 95% specific, it means if you don't have the disease, there's a 95% chance of getting a negative result in the test. Yeah? Do you remember these words? Yeah? These are useful words to remember in your future career. Okay? You might want to remember that. If you're reading a paper or a test or something, you know, it's good to know if the test says it's 90% sensitive or 95% specific, what those words mean. Oh no. No. Okay, you're looking confused. I'll write it down. Alright, so look. You have the disease. You would like the test positive for the disease. This is called how sensitive the test is. Okay? You don't have the disease. You would like to know the probability of getting a negative result in the test. This is called how specific the test is. Why might these be different percentages? You know, you might think, oh, it's just accuracy, it's the same number. But, you know, in real life, why would these be different? Yeah, but, like, give me an example. You know, if you're testing for something.
Oh, for example, if you don't have any disease and you'll have a positive result.
Yeah? But, like, I mean, what might be a cause for making these different?
Because they can have symptoms with the disease.
Lifestyle, no.
They can have symptoms with the
Like
disease,
systematic
or
ones.
we don't have disease.
I don't think you quite know. Have you done blood tests in biology? No. So suppose I was testing for a virus or blood poisoning or something like this, right? You put the blood sample under a microscope, we'll say, and you look for the presence of the virus. Okay? If you see the virus, then you probably have the disease, right? And I mean, if you have the disease, it'll probably show up on the blood test, okay? But just because you don't see the virus, does that mean that they're, you know... I mean, if you don't have the disease, is it possible to get the negative result? Yeah, it just means in the blood sample, maybe, you know, not enough of the cells showed up. Do you know what I mean? Like, I mean... And there's also human error as well when you're reading things, you know? So, I can see these being quite different. I would imagine that this one is probably...
99.9.
Yeah, I don't know. It depends on the situation.
True negative is better.
I would think.
True negative is better.
I think this one would be higher. Because think about it. If you don't have the disease, right? The person looks at the blood sample and says you don't have the disease. That should be quite high. Yep. No, actually, I'm not sure. I'd have to think about that. Oh, it's something worth thinking about. Anyways. These are not the same, and I think usually when I'm looking at these numbers, yeah, I think this one's usually the higher one, but it's going to depend on the situation. I don't know. I can't remember. What I do remember for a fact is that they're definitely always different. That is certainly true, and depending on the situation, will determine which one's higher. So let's have a look at an example. Right. Let's say this is disease and this is test positive. Okay, so let's say, I'll just make up some numbers here. 0.2, 0.3, 0.2, and what am I at? So this here has to be 0.3. Okay, so let me give you a simple enough question here. What is the probability that a person has the disease given that they tested positive for the disease? So the person walks in and they have a positive test result in their hand. How likely is it that they actually have the disease? Calculate that for me. Yeah, it's 0.2, isn't it, over 0.5, which in this case here is 0.4. Yeah? Okay. Next calculation. I want you to tell me how sensitive this test is. How sensitive this test is. So what is sensitivity? Probability of getting a positive result given that you have the disease. That's 0.2 over 0.4, which is 50%. Now, tell me how specific this test is. So that would be negative given no disease. So that's what over what? 0.3 over 3.6 or 0.3? 0.3 over 0.6, isn't it? So just by coincidence, this test is also 0.5, by coincidence.
Can't you do that 1 minus the 0.5?
Yeah.
Just no way.
For the first one?
No, to get the third one, you do 1 minus the second, also the second one.
There is no relationship here between them. The numbers are just coincidence. So for example, are you saying if you do 1 minus? If you do 1 minus on this one, what do you get? You get the probability of not having disease given that you test positive. If you do 1 minus here, that's a probability of a negative result given that you have the disease. And if you do 1 minus here, what's that? Probability of positive result given that don't have the disease. None of these are the same as any of these. So there is no link between these, like you suggested. Yeah? The second one is the sensitivity, how sensitive it is, and the third one is how specific it is. Okay, continue. Yeah? Okay, let me give you, I just want to do 2 from the book, an easier one and a hard one. Can you just for a moment try number 7, which is not too difficult, and then we'll do a really tough one after that. I'll give you the answer in a moment. Guys, come on, try number 7 here.
6 and 7.
7. Okay, have you got 7 there? That's- One quarter of people have a dog and 1/5 of people have a cat. 3/5 of people don't have a dog or a cat. So I'll start with the outside here, 0.6. Okay? Now it might be good to call this one here X. And this piece here should be X. How many have a dog? A quarter, isn't it? 0.25 minus X. And how many have a cat? A fifth. So this is 0.2 minus X. Now what should those 3 numbers add up to?
4.
Yeah, just the 3 of them should add up to 0.4. All of them should add up to 1. So 0.25 minus X plus 0.2 minus X should equal 0.4. Cancel, cancel. 0.45 minus X equals 0.4. So X equals,
0.05.
yeah. So what was I looking for? What is the probability that a dog owner is also a cat owner? Now what probability is that? I mean as letters.
C, D.
C and D?
Yeah. C, D.
But, no, yeah, well what's that called, Ray? Yeah. So, what is the probability, no, not intersection. What is the probability that a dog owner is also a cat owner? So that's C given D.
Looks like it was just that.
No, that's not the same. No, this is different. So that would be cat and dog, which is 0.05 over what? Dog, isn't it? Yeah. So, what's that? 0.2? Well, the question was, David, it said, what is the probability that a dog owner is also a cat owner? So you know they're a dog owner. Definitely. That's not in question.
Yeah.
You want to know what's the probability that they also have a cat?
Oh, I thought it was like and.
Yeah, no, also and are different words. Yeah.
Yeah, so I just.
Yeah. If I said, what is the probability that you pick someone who's a dog and cat owner? That would be 5%. 5 is different to 20. And is different to also. Are we all having an okay day today?
No, but this is like.
Words have meaning.
Yeah.
Different
well,
words have different meanings.
I've seen a question that it was and.
Yeah, okay, that's okay. I'm only trying to annoy you. Yes? Shh, hang on, I can't hear. Say again? Say again? In this one? Yeah. People who have dogs and cats, yeah. And inside is both, and outside is neither. Yeah? But just to be clear, if you're here, what have you got? Just the dog.
Yeah.
And here?
Just the cat.
And here? Both. And here? Neither. Yeah. Yeah? Okay, I'll give you, yeah?
When we are finding x value, we have to include 0.6.
I did in my head because that's why I said it adds up to 0.4. Right?
I'm one of them.
Yeah. What, you're in here, is it?
Yeah.
Oh, congratulations.
I'm 0.6.
You're in this, oh, you're in this, okay, alright.
Yeah.
Yeah.
What's the set at 0.6?
Say again?
What's the set at 0.6?
Oh, no, if you want to include the 0.6, then what you would have to say is plus 0.6 equals 1.
So don't we have to put that plus 0.6 minus x is equal to 1?
This plus this plus this plus this equals 1.
So we don't have to write 0.6. We don't have to minus x value from 0.6.
This the 0.6 was given in the question. I said 3/5 don't have anything. Yeah. Is that okay? Is it? I don't even know if you're ready for this harder one. We'll see. Try question 13. Is there an echo in here? 13, yes. Now, if you need a little bit of help, just to be clear with the English, if I say if one of the children is a boy, I'm not saying that only one of them is a boy. Just that you know one of them is a boy, but it's still possible that both are boys. Yeah.
But,
The example, the story that this comes from in part B says, what is the probability that a married couple has two sons? And I deleted it, but in the story it was, if one of the children answers the door and it's a boy. So when I say if one of them is a boy, that just means that, you know one of them is a boy, but you're not saying that exactly one is a boy. The other one could still be a boy. Yeah?
Alright.
Yeah?
Oh, I didn't finish, I gave up.
Okay. In a sec, yeah. Yeah, the first one is what? 1 over 2. Yeah. So if we look at the first one, what is the probability that they have two boys, given that the eldest, or if you want to think about it this way, the first one is a boy. Yeah? I think you all got this. So that's the probability of having two boys and the first is a boy, all over the probability that the first equals a boy. Now, I think you all caught that if I say, oh, what's the probability of having two boys and the first one is a boy, then that really is the same thing as saying, what's the probability that... No, come on. Come on.
What was the second one?
That the second one is a boy. Listen, you need to listen, okay? Probability of getting two boys and the first is a boy. Yeah? So what's that saying? Same as getting...
0.5, 0.5.
Yeah, that's it. Two boys.
No, it's not. Well,
Okay, stop. If you want, you can think about it like this. This second piece here, that the first is a boy, is not really necessary, because I just said here, two boys. Okay? Suppose I said to you, flip a coin twice, and you want the probability of getting two heads, and the first result is a head. Did I really need to say the second part? Did I? No. No, I didn't. It's not important. If I said, what's the probability of flipping a coin twice and getting two heads, and that the first result's a head? Exactly. So the second piece here, not necessary. Two boys over the first is a boy. Okay, so let's fill it in. What's the probability of getting two boys?
0.5 squared.
Yeah, which is 0.25.
We'll divide by
Now, you just told me this. Didn't she just say a minute ago 0.5 times 0.5? Come on now, guys.
So can you draw the Venn diagram?
Yes. Or a tree diagram. Boy, girl, boy, girl, boy, girl. This and this. What's that?
0.5 minus 0.5 minus 0.65.
Yeah.
We don't even need to complete.
Yeah.
And then first is a boy?
0.5.
0.5, isn't it?
Yeah.
Yeah. So like what's... Yes?
Yeah.
Yes? It's just English, right?
Yeah.
English, you speak it, right?
Just Monday.
Just Monday.
Yeah.
So we got
You watch, have you ever seen the movie Pulp Fiction? Isn't it? With Samuel L. Jackson. You know that line in it? English, you speak it. Question mark. There might have been a swear in there too. Do you know the line I'm talking about? No, okay. You know the one I'm talking about? Yeah? Okay.
I should know, but like in Ukrainian.
Okay.
I have those things that you know in Ukrainian.
I don't know it in Ukrainian. Right, can we do the next part?
yeah. That's why this.
I'll make it a little easier. I'll do it on the Venn diagram. Okay, can I scroll down? Yeah. So look, here's the situation. You can start off with boy or girl, and then boy, girl, boy, girl. Here, 0.5, 0.5, 0.5, 0.5, 0.5, 0.5. And the story is, what's the probability, once again, that you have two boys, given that at least one is boy. Okay? Remember I said if one of them is a boy, we just know one of them is a boy. Like one of them came to the door and we could see that one of the children's a boy. Okay? So, if you look at this Venn diagram, I have 4 situations. 1, 2, 3, 4. How many of those situations is represented by this? At least one of them is boy. 3 of them. First one, yes or no? Yes. Second one? Yes. Next one? Yes. And last one? No. So, that's represented here. Okay? And how many of them is it that I want? Just the first one. Okay, so if I just use a little bit of letters here, if I change this into A given B, this, and this fall into the group of B. And which ones fall into the group of A? Just the first one. Okay? So according to the formula, it's A and B over B. Good, good. Now, how many of those are A and B? No, just tell me how many. 1, 2, 3, or 4?
4.
Just one. Which one? And what's the probability? And how many of them are B? 3 of them. And what's the total probability? 0.75. And so in total, what do we get? 1 over 3. Yeah. So can you see how sometimes for these questions it's easier to draw a Venn diagram, and sometimes it's easier to draw a tree diagram? What might be a rough tip or a rough rule to decide which is a better diagram to help you? Pretend that you're doing an exam and time is of the essence. Guess. No.
How did we calculate this point?
No, answer my question first. Is there any way we can know when it's easier to do a Venn diagram and when it's easier to do a tree diagram?
Anything repeats?
Yeah, no. They don't have
Consider
this
the
section.
consider the values.
No, I don't think anyone else.
Something like that.
Yeah. Okay, the key word here is sequence. Okay? If the events form a sequence, then you should do a tree diagram. For example, is having one child and then having a second child better described as being a sequence of events or 2 events happening at the same time? It's a sequence. So we should use a tree diagram. Now remember when we did examples of pulling out a card from a deck and you want to know if it's a queen and a red?
It's not a sequence.
It's not a sequence because it's happening at the same time. The card is, it's also like with the cat and the dog owner. Okay? If somebody is a cat and a dog owner, they're a cat and a dog owner at the same time. So that is more accurately represented by a Venn diagram. Okay? But if my question was something like a person goes into McDonald's and they buy a coffee and then they could choose to buy a cookie with it or something, well, that's a bit more
Kind of sequence.
represented by sequence, because first they buy either a coffee or they don't, and then they go on to either buy a cookie or they don't. Yeah? Can you see the natural difference
Yeah.
between the two stories?
Yeah.
Yeah. So I think in this question here, it was a little bit easier to think of it as a tree diagram, because you have first child, second child.
Yeah.
Yeah. Okay. That one was very difficult. You won't get one as difficult like that in the exam. But the question we did before that with the cat and the dog owner, or the question we did about the disease, these are standard exam questions.
So which?
So really you should be able to do up to 12 in this. So is the problem language and that it's Monday? And is this your first class as well? What was your first class?
English.
The
Say
language,
yes first.
the language part of your brain wasn't activated by 2 hours of EAP.
No, it's finished.
Oh, the English part of the brain is shutting down now into power saving mode. Yes, okay, I see. Right. Can you try these questions for a few minutes and then we'll go on to the next lesson? These are all important for the exam.
1 to 12.
As I just told Nikita 30 seconds ago, 1 to 12. The guy sitting right beside you. Nikita. Yeah.
Excuse me.
Yes.